Okay, so I will just state, most of you have probably seen this in different classes, but I will just go straight with the strong form. So we're going to go very quick through the heat equation in 1D so that you see how easy it is. And this is going to help you also to remember what we have done already for the elasticity case. It's going to remind us how easy it is to get from the strong form to the weak form all the way down to the discrete equations. So for the strong form, we say, well, given our conductivity K, we're going to call it K, that is a scalar. Yeah. Now we're going to have a heat source F. That is also a scalar function. We're interested in finding the temperature field such that, and I'm going to write down my equation for the heat conduction problem, and this has to be valid for all x in omega, right? If you remember Fourier's law describes the heat flux with respect to the gradient of the temperature field, right? This is a what you see here, this equation is actually the Poisson equation. It's called the Poisson equation. And of course, that alone is not enough to solve the problem. We need also the boundary conditions, as you remember. So boundary conditions, as you know already, can be defined on the primal field, or it can be defined on the dual field. And we also said that there is a combination between the two that we call convective boundary condition. And is equal to H, which is our heat transfer coefficient, and then this U infinity is the ambient temperature, which is basically your reference temperature. So I'm going to need some space here. Gamma H. And as you see here, we have again our N, okay? And if you remember, we use that N in the case of elasticity for what? Huh? Not really direction. It was our convention for what? Huh?
Sign convention?
Yeah, it was the sign convention to specify what would be the sign of our axial force at the location of a node, right? And we said, well, that N has to have the value so that it gives me the right physics to the problem. And we said, well, if that force is producing a compression, right? So then that N was going to have a value that was going to make this whole axial load go in the x direction if it is applied at the left node. So that was the whole thing that we did for the elastostatics case. But now for the heat, the convention is also very simple. So it is positive when we have heat flowing out of the bar. Okay. So
clarification, U is temperature, right?
Yeah, in this case it's temperature. Yeah. So we are always going to define U as our primal field. In the case of elastostatics, that was a displacement. Now we're talking about temperature. Okay, so that is our sign convention. So we can make a very simple diagram here. Let's say this is our bar, and now we have a temperature field that looks like this, right? Where this is our value of T1. So this is my point 1. And this is my point 2. So Q1 is going to be minus A1, okay. A in this case is the area. T1 divided by L, that is the length of the bar. And Q2 so you see that because the gradient is negative, right? Then where is the heat going in this particular case? If we take a look at this node here, where is the heat going? It's into the bar, right? And because it's going into the bar, we said that our convention was going to be what? Positive or negative? Negative. Negative. And so, because the gradient is negative, right, our n value there is going to be what? Huh? Positive. So it's a bit tricky to figure out, but once if you do this plot and then you see where heat is flowing, if we want that convention, that heat, if it is flowing out of the bar, it has to remain positive. That's what's going to give you the right sign to that term for the boundary condition. Yeah. Let me copy this again, but let's gonna do it with a different. So we're going to do it the other way around. So now we're going to have a temperature distribution that looks like this. Okay? And of course, as you would expect, this would have the other signs, right? Yeah, because in this particular case, the gradient is positive or negative.
It's increasing.
Yeah. So if it is increasing, and I take a look at the right point, right? Where is heat going? Outside or inside? Huh? Inside. Okay, that's why on the right hand side you have a negative. Anyways, it's just a matter of convention. You could have chosen the other way, but as long as you are consistent, it's just fine. Yeah.
Sorry, the triangular shaped letter, what is that?
Triangular shaped letter?
Well, for instance, you take Q1 equals minus.
Oh, that is the area, right? So you're taking a look at all the heat that is flowing through. So let me write that down. Yeah, this is area. Okay, so But of course, let's not spend too much time on this. It's just a subtlety. What we really want to do is to get to the bottom of our equations that we can actually solve it, right? So who remembers how do we do this? If I ask someone to come here and get me the weak formulation, you think you can do it? Who's brave enough? Who's brave enough? Come on, guys. I will help.
Weight function.
Huh?
We can multiply with the weight function and integrate.
So that means that you want to... Okay, so let's see what you're saying. So if we take our equation, right? It's a Poisson equation, so we say, well, my equation is k, the second derivative, plus f. This is my equation. And then we do what?
Multiply with the weight function.
I multiply with the weight function. And then we do what?
Integrate over the boundary.
Integrate over my domain. Yeah?
And set it equal to 0.
And then set this equal to 0. And this has to be valid
For all the values of the weight function that are members of the energy space.
Okay, nice. Yeah. So, very nice. It's very simple to write what we called the weak or variational formulation. And as we said, for the elastostatics case, the same thing applies here. It's all the same. So the idea is that we are basically satisfying that Poisson equation on an average sense throughout the bar. That is the whole idea behind it. Okay. So contrary to the strong form where we had the Poisson equation plus boundary conditions, and finding a solution to that would satisfy that equation everywhere, exactly along the bar. Here, we're just satisfying that on average. But can we solve that yet or not? What did we do? What did we do last time for the elastostatics?
Integration by parts.
Integration by parts. And why did we do this? You lower the requirement of differentiability on your trial solution. So let's do that. So if we take that first term, right? Well, if you remember, integration by parts was u dv uv minus v du. So my integration by parts plus let me see, let me remember here dw dx, okay, du dx is equal to this is another way to write integration by parts, and of course what we have here is just this whole expression that needs to be evaluated at 0 and at L. Yeah, so if we plug in that back, what I'm going to do is some arrangements, some rearrangement of terms, because here we're interested in that term which is showing up here. So what we have is that we're going to have and that is going to be equal to the fourth term. We have to multiply that by the weight function, and then we're going to have the effect of the boundary conditions. Right, and if you remember, this guy here was actually defined as our heat flux. So from this expression you can again say that, well, this can be defined as my bilinear form, and this whole thing is my linear form, right? Because even though this guy has a dependence on u, that's actually something we know that is the heat flux, okay? All right? And so, again, our weak or variational form can be written very simply in the same terms as we did last time. Find u in some space, let's call that space V, such that the bilinear form is equal to the linear form for all W in that same space. That, if you remember, we defined that space very nicely last time. We said, well, I want that space to basically already be zero at all the parts of the bar which have directly boundary conditions, because we really want to remove that reaction force in the case of elastostatics. In this case, you can call it reactive flux, or if someone has a better name for that. Okay, reactive flux it is. Yeah, so that V, remember, it was defined as a set of functions V such that V evaluated at the portion of the domain gamma u is equal to 0, or the restriction of V in gamma u is equal to 0. Okay, so that's it. That's all we had to do to get our discrete, sorry, the variational form. But again, we said, can we solve it at this point? Yes or no? No. Yeah.
I don't really understand the third line, basically.
This line.
Yes.
This is integration by parts.
So you're going from the top line?
So what I want to do is to lower the differentiability requirement of that guy, right? Yeah. So you can. There are many ways to do this, right? You can identify from this equation here which one is u and which one is dv, right? And for example, if you see that what I want is my u to be this one, and my dv to be that one, right? Because that is what is going to reduce the differentiability requirement when we write this integral of v du. What I normally like to do when I look at integration by parts is, well, if I'm applying the derivative, right, to something that is a product, well, you have to do w du the second ux squared, and I assume that, okay, I just differentiated that guy, right? And then I have to apply the derivative to the other one, right? And this would be basically applying the derivative to that. That's for me much easier than just identifying terms in integration by parts. Yeah, and that's how I wrote this. Anyways, you try it and you see it's very straightforward. Any other questions before we move on? We said that we cannot solve this. What do we need to do?
Limit what kind of W should.
Yes, because we are still working in an infinite dimensional space. So that what we said is that we're going to look into a subset of that space that we call the finite element space. Okay. So now, if I take this equation and I say, well, maybe I write it so that it is in the notes. I have both, right? So we obtain the discrete equations by taking UH and WH from some space that we're gonna call VH, that is a subspace of this V. Okay, so if you do that, then our problem becomes just like that. Oh. Okay. Okay. And the rest is straightforward, right? We took, and I'm going to go very quickly through this because we want to go and take a look at the three-dimensional case. But then what we did is, remember, we take UH as the sum of VI, UI, WH as the sum of VI, WI. We plug that in, and in the process, that is going to take us to our discrete system of linear equations. K, U is equal to F that we solve for U. Same thing as we did before, now that we go very fast because we all know this at this point. And if you remember, well, my K, it could also be obtained as an assembly operation with all the number of elements. So this NEL is the number of elements of local contributions. Remember that all of these are K is a matrix, U is a vector, and F is a vector. And then our F can also be obtained as the assembly of all those local force vectors. All right? Very straightforward. And now we can solve a problem. But this is not really what we're interested in now. We're interested in the heat conduction for higher dimensions. We still have plenty of time, no? Okay, so this is where things are going to get slightly complex for the geometry part. So normally, well, when we're dealing with higher dimensions, just a reminder of a few things that we want. If we compute the gradient of a scalar, right? Let's say S is a scalar, and a scalar function, and I compute the gradient. Yeah, by definition, this is the derivative of S with respect to xi, ei. Those are the base vectors, right? If we compute the gradient to a vector field, that's the derivative of the ith component of that vector with respect to xj ei tensor ej. So that is a tensor. Let's move this here. Now, if we're talking about the divergence operation, just as a reminder, right? So the divergence of a vector field is going to be what? It's going to be a scalar field, and it's defined as Vi xi. Notice that of course, I'm applying the Einstein convention. And then if we take the gradient of a tensor field, what is that? Sorry, the divergence of a tensor field is what? It's a vector. And it's defined as we take the derivative of the ijth component of that tensor with respect to xj and then ei. Yeah, so now that we're working in higher dimensions, we're going to be dealing with tensors and vectors. And that's perhaps the only complication because everything else is going to remain the same. So if we take our mechanics potato now, right? So we draw our mechanics potato, and then we say, well, now there is a portion of that boundary that I call gamma u. And if you remember, what was gamma u? Dirichlet boundary conditions, correct? So this is my omega. Then there is another portion of the boundary that I'm going to call gamma h, and this is where we're applying what type of boundary condition? The mixed, or the Robin, or the convective boundary condition, and the rest is gamma t, which, as you know, is the part of the boundary where we apply Newman boundary conditions. And normally, the way you're going to see this over and over, well, you're going to say that this is the way you define the boundary, right? So it's basically defined as the closure minus the open set, right? It's going to be composed as the union of different sets, gamma u, gamma h, gamma t, right? And I do that because I want the closure of that. And you are going to also see that gamma u intersection gamma t intersection gamma h is equal to the empty set, which also says, as we said before, that these are just mutually exclusive sets. So they are there is nothing, they are not superposing at any point, right? Okay. So we are ready. So what is a strong form? Now that we have our conventions, a strong form is, well, again, we're going to list our different parts, the different components of our equation. We talked about the conductivity. Well, the conductivity in higher dimensions is actually a tensor. So the way you say a tensor in mathematical notation, you say that is defined in, again, the domain codomain notation in omega bar, and it's actually going to a tensor field, which is represented by this. Yeah, so this is a d by d tensor. That is the way this is expressed in mathematics. Yeah, so we have now our force or our source vector. It is still a scalar field. Then we're going to have a prescribed displacement that, of course, goes from gamma u and it's a scalar field. We're going to have our heat flux, gamma q, and it's also a scalar field. And then you're going to have your h, or your heat transfer coefficient, which is defined in that part of the domain where we need to apply that type of boundary condition. And so given all those quantities, find u, find the temperature, which is still in higher dimensions a scalar field, right? Such that, and now we're going to write our equation in higher dimensions. So we have the divergence of k grad u plus f is equal to 0 in omega. So that is the equivalent to higher dimensions, yeah?
So f is a scalar space?
Scalar field.
Dimensional,
It's a scalar field.
scalar field.
Yeah.
But this is only for heat conduction.
For heat conduction, yeah.
Yeah. Because for
For mechanics, we had a body force,
yeah.
and that was a vector field.
Yeah, exactly.
But here we have a scalar field.
Yeah.
So if you see this equation, one second. If you see this equation, well, we have a scalar field. Well, grad u, I put it, the bar is down because the whole expression is a vector, right? So u is a temperature, is a scalar field, but grad u is a vector. And if we take the divergence of a vector, we get what back? A scalar field. So we have scalar plus a scalar. Your question?
Yeah, I was wondering how this same holds for the flux. Right? The flux is a scalar in this case, not a vector.
The scalar, no, it is a vector.
Oh, right.
It is a vector. Did I say? So the heat flux, yeah. The thing is that, look, the expression k grad u, that is a vector, right? Because we're taking a tensor that is operating on a vector, so the result is a vector. But then you are dotting that to n, right? N is a normal to the domain, and that is going to be a scalar, right? Because you have vector dotted with a vector that gives you back a scalar, and that's why this q bar is a scalar field. But you are confused, I think, by this grad u. But we're going to look at this because now we're going to write the boundary conditions. So that is, of course, not yet the full strong form. We need the boundary conditions. So we need u is equal to u bar on gamma u. And this is what I was telling you right now. So if we take k and we dotted that with grad u, right? This whole expression is a vector, but this is dotted with a normal to that boundary. and that gives you back the heat flux, right? And this is on gamma q, and then we have finally the convective boundary condition, which looks very similar to this, is equal to h, which is a scalar field, u infinity and beyond, kidding, on gamma h. Okay, and that is our strong form of the boundary value problem. Yeah?
What is gamma Q?
Gamma q is the portion of the boundary where you're applying the Newman boundary conditions. We keep the same notation as we had for the bar in the 1D case. So our omega is our domain. Gamma u is a portion of the boundary where you are enforcing Dirichlet boundary condition. Gamma q, you're enforcing Newman boundary condition. In this case, it's not gamma t because t is traction in the elasticity case, but now we are enforcing q, which is the heat flux, but it's still the Newman boundary condition. And then gamma h had the same notation as before. Okay? So, very straightforward to get the strong form. Now we want the weak form. And again, who can tell me? How do we get the weak form? Someone else? Yeah. No one? No one?
Take the integral of the equation.
Yeah, yeah. So we take the equation. We take the equation. K grad u plus f. And what do we do to that equation? By a weight function, which is what? It's a scalar, a vector, a tensor. What is the dimension of my differential equation? What is it? It's a scalar field or a vector field or a tensor field? It's a scalar field. So I take a scalar. And then I integrate over the domain of interest, which is omega, d omega. And now that we're going in higher dimensions, omega, d omega is going to be the integral over the inside of our domain, and gamma is going to be the boundary. Okay? And this is going to be equal to 0, scalar or vector, or tensor? Scalar. And this has to be valid for all w, again, in some nicely defined space of functions that we know how they look like, right? We are just going to take functions, and we're going to make sure that those functions are going to be 0 in that part of the domain where you are enforcing the displacement, the temperature. Okay? Sounds good? So now, what do we do? So that you see this exactly the same thing as before. What do we do? We do integration by parts, right? And you're going to have to trust me on this one. You can check this later, but you can prove. And this is, again, I like to do this in, while applying the derivative to something. Well, in higher dimensions, if I want to take that first term and I say that w, and then I take that whole thing, right? And then plus, so I have a scalar, right? And then I have this other whole thing. We have grad u, which is a vector multiplied by a tensor, still a vector, but when I take the diversion, it's a scalar, right? So I have the product of two scalars. Well, this whole thing is actually, if you want to apply the same idea to the first term, I want to apply the derivative to the first term. So you're going to see a gradient, right, of that w, but the gradient of that w is a vector, right?
Yes.
Yeah, so then this dotted with that other vector, right, is going to be equal to applying the divergence to that whole thing, w, and then the divergence of k grad u. So this, you have to trust me. or you can go and then in component form you're gonna be able to show that this is true, right? All I want you to see right now is that it's very straightforward to understand that this is correct. If we have again, let's say two quantities u and v, right, and I want to apply the derivative with respect to x to this, well, du dx plus dv vx, sorry, v and then u, right? It's as straightforward as doing that. Now, if we do that in higher dimensions, what you see here is that if I take this term, I am just applying the derivative to the other term. So then what I do, okay, so I take this thing without applying the derivative there and apply the derivative to the other term, which is in this case our weight function, which is a scalar field, right? So this whole thing is now a scalar. So I have a scalar here and a scalar here. And then that is by definition applying the divergence to that whole expression. And that is what we have here on the right. Yeah. You can also prove this in component form, but let's not spend too much time there. So if we plug this back into the equation, right, what do we get? Well, all we need to do is now plug this guy, which is this one. So what we get is, I'm going to move it to the other side because it's going to be negative, but then I'm going to move it to the other side. So then we're going to have an integral that looks like this, and this is on omega, and then that is going to be equal to my original. This, we did not touch that term, so it's going to be WF, also integrating on omega. And then we're going to have the integral of this guy here, right? So I'm going to say the integral of omega of the divergence of all that term. Let's move everything back. D omega. Yeah, and now we have, this is our new expression. Yeah, but now, yeah, you were going to say that that is Q.
No, you didn't use K in the first.
Oh yes, we're missing K there, definitely. Thanks for that. Thank you. Okay. And now if you take a look at this term here, we're applying the divergence, right, to that expression, and that whole thing is being integrated. And you may remember from another class, there is a nice theorem that is called Divergence Theorem that can transform that integral into the entire domain to just an integral that is happening over the boundary. So if we take that guy here, this is actually the integral over the boundary of whatever we have inside that divergence, which is W. What am I doing wrong here? I'm doing something wrong. Let's see. Yeah, that's fine. It's the same. Okay. This guy basically dotted with the normal vector to that domain. Yeah? Let me see if I have it right. No, I have something that is not right here. This is not right. That was wrong. W, missing a K here. Yeah, dotted with N. Yeah, that's it. And remember that this whole thing that we have here was our heat flux Q. Yeah, so there was a mistake there. I had somehow a divergence on the right-hand side that did not make any sense. But now that we have transformed our basically our integral over the inside of the domain to an integral over the boundary, then we can replace that because we know that that expression here is just the boundary condition, right? Our Newman boundary condition. And so if we rewrite this equation, what we get is grad U is equal to the same plus in the case that you have only a flux boundary condition, and if you don't have a flux boundary condition, then that guy Q has to be replaced by the two components that define the Robin boundary condition, and then you would have another expression. So if gamma Q, and then we will change that we're going to go through this one more time. So if you are a bit lost, we are going to go through this again, okay? Gamma Q. And then plus the other component of H. Okay. And that becomes our new equation. So this one here on top, this expression, it's only the equation if you have just a Newman type, but if there is still another part of the boundary where you also have a convective part, then you also have to add those terms that correspond to the convective part, which are this one and this one. Again, we're going to go through this soon, and of course all of this has to be valid for all W's inside some space. Once we have this expression, we can readily identify what are our bilinear and linear forms, because everything that is on the left that depends on both U and W, that is our bilinear form. Everything that is on the right is something that we either know or does not depend on U, so that's our linear form. So all of that formulation translates into find U into some space such that BUW again is equal to L of W for all W in some space, and you can already see that this expression here is going to be my bilinear form, and all of these is going to be my linear form. Okay? So let's go back and see what we just did, right? So to get the weak formulation, we just grab our differential equation. Here, we weighted with some weight function. We integrated over the domain, and we set that equal to 0. And then we did what would be the equivalent to integration by parts, because we want to lower the differentiability requirements. So we came up with this expression. And then when we plug that in, what we end up with is a term where we're applying basically the divergence to that WK grad U, and there is this nice theorem that is called the Divergence Theorem, where we can convert that integral over the entire domain to an integral over the boundary. So we just take whatever is inside the divergence, and then we dot it with the normal field, and that's where our natural boundary condition shows up. And again, in 3 dimensions, it's exactly the same thing as in 1D, where you see that your boundary conditions are showing up naturally in the formulation when you go through these steps of integrating by parts and the divergence theorem. Okay, and that was it. The only thing that we do after obtaining this term is just replacing by the boundary condition. So if you are dealing with a problem that has only a Newman boundary condition, what you get is this expression here. You see there is no gamma h there, only Newman type of boundary condition. But if you have a convective boundary condition, then your formulation gets a little bit more complicated. So it has 2 additional terms that are showing up from the 2 terms that define the convective boundary condition. And that's it. That's basically the heat conduction in 3D. Again, the same steps as we did before to get the system of linear equations does not change from this point forward. So we get the Galerkin formulation, the finite dimensional form, right? We take these U's, the temperature, and the weight function from our finite dimensional space, or our finite element space. And then we plug that into the bilinear form. We get the stiffness matrix. We plug the weight function into our linear form. We get our force vector, and everything remains the same as before. Okay? In 3D, what we do actually, we are going to, well, there is a definition that is slightly more formal in the book chapter, right? So let me see if we have time to talk about this. How much time we have? 5 minutes. Do you want us to go again through the whole discretization process from this point to get the discrete equations, or since it is the same as before, it's okay for you? Yes? Okay. Okay. All right. So we have 5 minutes. Let's see if we can make it. Okay, as we said, we take the trial, solution, and our weight function. So we have UH So what we're going to do is we're going to just represent UH as, let's do it in matrix form. So that's going to be the product of a vector phi that contains all the shape functions. And we do the same. And this can be written again as this, right? So if we take our bilinear form now, the idea is to solve this equation. And so what we're going to do is we're going to plug that in to that equation. And what you get is something where we're actually applying our bilinear form to our shape function vector, right? And this has to be, because that we make this change, And now it's not for all w, but we actually express w as the product of the shake function vector times the coefficient w vector. Then this has to be valid for all coefficients in some Euclidean space. We really don't know how many degrees of freedom we have, so I call it Rn, and n is going to be basically the number of degrees of freedom that you have in your problem. So that depends on the number of elements that you use to discretize your domain. And so since that has to be valid for all vectors w, then of course we have this has to be satisfied as well. And as you remember, this gave rise to our k, and this gave rise to our f. And we keep the same notation as we had before. And so that is what we end up with. So I don't think we have time to go to from the other direction to do the equilibrium from a one element. But it is exactly the same thing as the one-dimensional case. It does not change at all. So now we can solve problems for heat conduction. We are not going to see anything for the project unless, of course, some of you are really interested in solving heat for whatever reason, and then we can discuss to do a modification of the project in that direction. Okay? Any questions? Yeah.
So when we write US in terms of P and capital U, U is a matrix, right?
U is a vector.
But UH is also a vector?
My? No. U is a scalar field, but then what you have here, this is the product of two vectors. It's a scalar product. It's just that in finite element terminology, normally you see it written like this, right? You could see it written like this, or you could also see it written like perhaps like this. This would make more sense. But in finite element analysis, everywhere you look at, right, you see it just written like this, but it is understood that here we're basically multiplying a vector, which is a row vector that contains your shake functions, and then U is a column vector, right? It's just, I also think it's slightly weird, but that's the way it is in the literature. So if I express something like this, then what happens is that in your force vector, you're going to see that this phi is not transposed anymore, and then you're going to start wondering, so why in the books that I read it does not match? You understand? So I try to follow the same type of notation that they do in finite element analysis. Yeah.
Wait, once more. U was a scalar, right?
The U is a temperature. That's a scalar field, right? Now what you have here is a product of two vectors. It's the dot product. It's a scalar product. So that's also scalar, right? So you're going to have phi1 U1 plus phi2 U2 plus phi3 U3 and so on.
And this gives you basically a number. So
It's a field. It's a scalar field. It's not a number. So this is going to be a function of x.
But were we talking in higher dimensions? So
Yeah.
why not a function of y and z as well?
They are a function of x, y, and z.
Oh.
So x, but I mean function of x,
Oh,
like
direction.
a point in space has three components.
Yeah.
A function of x for me is x, and it's a vector, right?
Okay. Then,
Yeah. Any other questions? Please go through the project. If there is something that is not clear, let me know. And remember, we have office hours also on Wednesdays. Yesterday, we only have one person showing up. So apparently, everything is super clear.